We will wait for a couple of minutes and maybe we can start at 7:05. Okay, so I will start today's lecture. So today we are looking at questions from GATE 2019 and the subject is heat transfer and the first question is question number 16. So the question, I will read the question. So consider the two countercurrent heat exchanger designs for heating the cold steam from T in to T out as shown in figure. The hot process stream is available at T in. The inlet stream conditions and overall heat transfer coefficients are identical in both the designs. The heat transfer area in design 1 and design 2 are respectively A1HX and A2HX. If heat losses are neglected and if both the designs are feasible, which of the following statements hold true? So In this question, we have been given two heat exchanger designs. So this is design 1 and design 2. Corresponding to them, we have been given the inlet fluid of tube side, that is F in, and T in is the temperature, inlet temperature of the tube side fluid. Similarly, T out is the outlet temperature of tube side fluid. And these parameters are same in both the design, except the T1 out and T2 out. So that is the shell side outlet of the shell side fluid temperature, outlet temperature of the shell side fluid. And we have been given this A1HX and A2HX. So given this condition, that is heat loss are neglected, and if both the designs are feasible, we need to find which one of the following options are correct. So basically, we have to find the relation between the area of both the heat exchanger and this outlet temperature that have been provided to us. So in this question, to solve this, you will just apply the energy balance and then compare the outlet temperature. And then again, based on the given data, you can comment on the area of heat exchanger. So we will see the video solution of this question. Hello everyone. We will be solving question 16 of GATE Chemical Engineering 2019 paper from the subject of heat transfer. So the question is, consider the two countercurrent heat exchanger designs for heating a cold stream from T in to T out as shown in figure. The hot process stream is available at capital T in. The inlet stream conditions and overall heat transfer coefficients are identical in both the designs. The heat transfer area in design 1 and design 2 are respectively A1HX and A2HX. And we have been given the general schematic. If the heat losses are neglected and if both the heat designs are feasible, which of the following statements holds true? Okay, so we have been given this heat exchange design parameters and the general schematic of the countercurrent heat exchanger, and we have to find which of the following options is correct amongst the given one. So let's solve it. So for design 1, let's just write the energy balance. So let's see. For first design, we can write the energy balance as mCp delta T, and here we have been given M as the mass flow rate as F in. So let's just write F dot in. Let's just write the heat capacity as Cp. So let us consider this as tube side and this one as shell side. So corresponding to that, we can write this for tube side fluid as Cpt, and the temperature difference is T out minus T in. Similarly, for the shell side fluid, I can write it as T out given as well. Similarly, I will write this for now secondary design. Here the flow rate and the other parameters for both this heat exchanger design were given as constants. I will just replace them as the same. The inlet and outlet temperature T in and T out same as the previous one. But in this case, the T out we have been given as T out 2, and in the earlier case it was T out 1. So we have been given that all of these parameters are same. All of these parameters are same. So from this, okay, so over here this T out, yes. So all of these parameters in first design and second design are same. So I think all of this can be cancelled out, and we can see that this term are the only different ones. So they must be same. So that is, we can write so we can write T1 out is equal to T2 out. Now from the given options, we have this option B and option C, in which the given options are, that is T1 out is equal to T2 out. Now we need to compare the area of heat exchanger for both of these cases. Okay, now in this is first design, this is second design, and in the second design you can see that this cold fluid T in is getting mixed directly to the outlet, whereas in the first design no such case is happening. So from this diagram that we can see that since the cold fluid is getting mixed directly to the outlet, in the second case this T out will decrease. Okay, so from that we can write it as T1 out is equal T1 out will be greater than this T2 out. So ideally this should have been the case, that is T1 out should have been greater than T2 out, but from the diagram we can see that both the temperatures are same. Okay, so from that we can see that ideally this T2 out should have been lesser, that is T2 out should have been greater, but since we are what mixing this cold fluid, the temperature is less, so ideally T should have been higher. T out T2 out should have been higher than T out. So for for design 2, we need to produce this higher T out. So for design 2 to produce higher T out, we need to increase the area of heat exchange. So if the area of heat exchange is higher, then this T output will be higher. That will be ultimately compensated by mixing it with this inlet stream. So yes, since we want to produce this higher T out, we need to increase the area of second heat exchanger. That is, area of second heat exchanger will be greater than area of first heat exchanger. Okay, so from this we are getting the area of second exchanger heat exchanger should be higher, and from the first energy balance we got that T out should be equal to T2 out. So yes, from here we can see that in the option D we are having the area of second heat exchanger is higher, whereas the outlet temperature of both the shell side fluid are same in option D. So yes, the correct option is option D. Okay, so we looked upon this question in which we had to find the relation between the area of heat exchanger and the T outlet. So again, to revise that, this was straightforward that T1 out will be equal to T2 out. But for comparing the area of heat exchanger, we observed that since in this case we are mixing the cold fluid to the outlet temperature, so in ideal scenario, since we are mixing the hot fluid to cold fluid, the temperature will decrease. But since in this case we have been given this T out, both are same. So in order to make both of these same, we must increase the temperature of the outlet stream, and that can be achieved by increasing the area of second heat exchanger as compared to the area of first heat exchanger. So after that, we will be having higher T out, and then again we will be mixing it with this cold fluid to again match this temperature as T out for both the design. If you have any questions, you can write in chat box, and then we can move on to the second question. So let's move on to the second question. So this is question number 42 from WinGate 2019 chemical engineering paper of the subject of heat transfer. And in this question, the question is a solid sphere of radius 1 centimeter and initial temperature of 25 degrees Celsius is exposed to a gas stream at 100 degrees Celsius. For the solid sphere, the density is 10 raised to 4 kg per meter cube and the specific heat is given as 500 joule per kg Kelvin. The density of gas is 0.6 kg per meter cube and its specific heat capacity is 10 raised to 3 joule per kg Kelvin. The solid sphere is approximated as a lumped system and all the specific heats are constant. If the heat transfer coefficient between the solid and the gas is 50 watt per meter square, the time in seconds needed for the sphere to reach 95 degrees Celsius is dash. So this is from the topic of unsteady state heat transfer, which involves conduction within the solid sphere and convection outside the solid sphere, whatever the object is, due to this, in this case, gas stream. So this concept you will find it in this lumped heat capacity analysis. So let's look at the video solution. Hello everyone, we will be solving question 42 of GATE Chemical Engineering paper 2019 and the subject is heat transfer. The question is, a solid sphere of radius 1 centimeter and initial temperature of 25 degrees Celsius is exposed to a gas stream at 100 degrees Celsius. For the solid sphere, the density is 10 raised to 4 kg per meter cube and the specific heat capacity is 500 joule per kg Kelvin. The density of the gas is 0.6 kg per meter cube and the specific heat is 10 raised to 3 joule per kg per Kelvin. The solid sphere is approximated as a lumped system, that is, Biot number is very less than 1 and all the specific heats are constant. If the heat transfer coefficient between solid and gas is 50 watt per meter square Kelvin, the time in seconds needed for the sphere to reach 95 degrees Celsius is dash. So here we have been given a lumped heat capacity system in which we have to find the time taken by the sphere to reach the temperature of 95 degrees Celsius given all the other environmental parameters. Okay, so let's just write what all things we have been given. So the radius of the sphere is 1 centimeter. The initial temperature, we will call it as T0, is given as 25 degrees Celsius and it is exposed to a gas stream at 100 degrees Celsius. So let's just call the ambient air as T infinity as 100 degrees Celsius. And for the solid sphere, the density is 10 raised to 4 kg per meter cube. So let's just call it as density of solid as rho s as 10 raised to 4 and the specific heat capacity as 500. Similarly, the density of gas, that is called density of fluid as 0.6 kg per meter cube and specific heat of fluid as 10 raised to 3 joule per kg Kelvin. Now Biot number is very less than 1. So this implies that lumped heat capacity is applicable. The specific heats are constant and the heat transfer coefficient, so that is H, we have been given as 50 watt per meter square Kelvin and at temperature is equal to 95 degrees Celsius. Time we have to find. So all these parameters have been given. So from the lumped heat capacity, we know that the formula of the temperature varying with time is given as T minus T infinity, that is my ambient air temperature, is equal to T naught, or T naught is my initial temperature of the solid body, minus T infinity, and this will be equal to exponential of minus H A into Cp rho V into time. And this area is corresponding to the solid. Similarly, Cp is of solid, density is also of solid, and Vs is also solid. So we will be using this formula to find the temperature, to find the time taken by the sphere to reach the temperature of 95 degrees Celsius. Okay, so let's just calculate first this term, As upon Vs over here. So As upon, so the surface area of the sphere will be 4 pi r square, whereas the volume of the sphere will be 4 by 3 pi r cube. This will get cancelled out, and this will be equal to 3 upon r. Now similarly, we will calculate the entire term inside the bracket, that is H A Cp rho s into Vs. So H we have been given as 50 into A by V we have 3 upon R, and R we have been given as 1 centimeter. So let's just convert it into meter. So it will be 0.01 meter upon Cp of solid. Cp of solid we have been given as 10 raised to 4, and the density of solid we have been given as no. Cp of solid we have been given as 500, and the density has we have been given as 10 raised to 4. So that will be 10 raised to 4 into 500. Okay. So we can simplify this, and this entire term will be equal to 3 into 10 raised to minus 3. Now let's just put this value over here, and we will get t minus t infinity on t naught minus t infinity is equal to exponential of 3 into 10 raised to minus 3 into t. Okay, and we will be having this minus sign over here. So now let's just replace the value of t naught and t infinity. It will become, we have to find the time taken by the sphere to reach the temperature of 95 degrees Celsius. So this will be 95. So let's just replace it. 95 minus t infinity was 100. T naught is the initial temperature, that is 25 minus 100. So this will be equal to exponential of minus 3 into 10 raised to minus 3 into t. So this we can write it as 5 on 75 is equal to exponential of, we can take log on both the sides, and that will give us ln of 1 by 15 equal to minus of 3 into 10 raised to minus 3 into t. So we can solve this equation, and we can get it as 2.708 is equal to minus of 3 into 10 raised to minus 3 into t, and that will give us time as 902.67 seconds. So yes, the time taken by the sphere to reach temperature of 95 degrees Celsius will be 902 seconds. So yes, the final answer is 902.67 seconds, and since we have to round up till nearest integer, we can round it as 903 seconds as the final answer. So in this question, we look upon this Lambda capacity analysis for the solid sphere, in which the temperature is a function of time, and at given temperature of 95 degrees Celsius, we had to calculate the time that was taken to reach that temperature. If you have any doubts, you can speak up or write in the question. I will wait for a couple of minutes and then move on to the next question. You can straight away remember this formula for any geometry that is available. So instead of sphere, if we have a cube or a cuboid, then also you can just replace the surface area, volume, and then use the same formula. And this formula will only be applicable if the Biot number is very less than 1. So if this condition is not given, then this formula shouldn't be applicable. That is, lumped heat capacity won't be applicable if Biot number is not very less than 1. Okay, so if you don't have any doubts, we can move on to the next question. So I will just quickly read the question. Stream A with a specific heat capacity CPA of given value is cooled from 90 to 45 degrees Celsius in a concentric double pipe countercurrent heat exchanger having a transfer area of 8 meters square. The cold stream B of specific heat capacity CPB is 1000 joule per kg Kelvin enters the exchanger at a flow rate of 1 kg per second and 40 degrees Celsius. The overall heat transfer coefficient U is equal to 250 watt per meter square Kelvin. Assume that the mean driving force is based on the arithmetic mean temperature difference, that is delta T MTD, is given by this formula, where Ti in and Ti out refer to the temperature of the ith stream at inlet and exit respectively. The mass flow rate of the stream A in kg per second is. Again, this is simple energy balance across the heat exchanger, double pipe countercurrent heat exchanger, but usually in most of the cases we use this log mean temperature difference. But in this question, we have been specifically asked to use this arithmetic mean temperature difference given by this formula as the driving force for the heat transfer. And given all this information, we have to find the mass flow rate of stream A. Let's look at the video solution. Hello everyone. We will be solving question 43 of GATE Chemical Engineering paper from 2019. And the question is, stream A with specific heat capacity CPA of 2000 joule per kg Kelvin is cooled from 90 to 45 degrees Celsius in a concentric double pipe countercurrent heat exchanger having a heat transfer area of 8 meters square. The cold stream B of specific heat capacity CPB is given as 1000 joule per kg Kelvin. It enters the heat exchanger at a flow rate of 1 kg per second and 40 degrees Celsius. The overall heat transfer coefficient U is given as 250 watt per meter square Kelvin. Assume that the mean driving force is based on the arithmetic mean temperature difference, that is delta T AMTD, is given as this formula, where T in and Ti in and Ti out refer to the temperature of the ith stream, where I is equal to A and B at the inlet and exit respectively. The mass flow rate of stream A in kg per second is dash. So for this given double pipe countercurrent heat exchanger, and we have been given this AMTD, so we don't have to use this straight temperature difference or log mean temperature difference. We have to use this arithmetic mean temperature difference as the mean driving force in this question. And the mass flow rate of the A we have to find in kg per second. So let's just draw a schematic in which this is my tube side. This is the shell side. Let's just assume that the A stream enters the tube. Okay, so A enters from here and leaves here, and we have been given as counter current heat exchanger. So we will enter from this side and leave from over here. And then we have been given Cp of A as 2000, and it is cooled from 90 degrees Celsius to 45 degrees Celsius. Whereas for the cold stream, CPB, we have been given as 1000 joule per kg Kelvin, and it enters at 40 degrees Celsius. And mass flow rate we have been given as 1 kg per second from here. So the overall heat transfer coefficient U is 250 watt per meter square Kelvin, and we have been given delta T AMTD. Arithmetic mean temperature difference is given, and the mass flow rate of A is like we have to find. So yes, for the A stream we have this inlet temperature and outlet temperature, whereas for the B stream we only have this inlet temperature. So we also need to find the outlet temperature over here. So let's just call it as T out. So we can write simple energy balance for the hot fluid, cold fluid, and the heat exchange across the heat exchanger. So that we can write it as so for the hot fluid we can write it as m dot h into Cp of h into temperature difference T in minus T out of, let's say, h. Similarly, for the cold fluid, we can write it as m dot c Cpc Tc in, no, it will be Tc out minus of Tc in, and this will be equal to the heat exchange across the heat exchanger. So let's just, it will be UA. Now we will be using arithmetic mean temperature difference over here. Okay. So now let us just equate the last two terms. So from here we will be getting, from here I think we will be getting the value of this. We should be getting the value of T out. So let's just write it. So the m dot c we have been given as 1 kg per second. 1 into Cpc we have been given as 1000 from here, and T out we haven't been provided, and T input is 40. So from this you can write 250 into area we have been provided as 8 meters square into, now we can find the delta AMTD. So that is equal to TA in plus TA out by 2. So it will be equal to 90 plus 45 by 2 minus TB in is 40 plus T out upon 2. So from here we can write this as 1000 T out minus 40 is equal to 250 into 8 will be 2000. 90 plus 45 by 2 will be equal to 67.5 minus of, let's just keep it as 40 plus T out upon 2. So we can solve this and we will get T out minus 40 is equal to 2 into 67.5 minus 40 plus 2 out, right? T out will be equal to 40 plus 2 into 67.5 was 135 minus of 40 minus of T out. This term will get cancelled and it will come to T out is equal to 135. So this T out will become 67.5 degrees Celsius. Now we will be using this energy balance between hot and cold fluid to find the required, that is the mass flow rate of A. So let's just write it as into T out minus CPC. So from here we can replace the values. So that is mass flow rate was 1 into 1000 into T out minus 40. M dot C we have to find CPC for the cold fluid. CPC is given as 2000 into temperature is changing from 90 to 45. M dot A will become 1000 into 67.5 minus 40, 2000 into 45. So yes, we can solve this and the final answer will become 3055 kg per second. So yes, the mass flow rate of stream A is given by this 0.3055 kg per second. And we have been asked to round up till 2 decimal places, so we can report the final answer as 0.31 kg per second. Hello. Okay, so we looked upon this question 43 related to this energy balance over this heat exchanger, in which we had to use this arithmetic mean temperature difference. So that was the only new thing in this question. We can move on to next question, and if you have any doubts, you can just speak up. I will straight away play the video. Hello everyone. We will be solving question 44 of GATE 2019 Chemical Engineering paper from the subject of heat transfer. The question is 20 centimeter diameter cylindrical solid pellet of a nuclear fuel with density 6000 kg per meter cube and conductivity of 300 watt per meter Kelvin generates heat by nuclear fission at a specially uniform rate of 10 raised to 4 watt per kg. The heat from the fuel pellet is transferred to the surrounding coolant by convection such that the pellet wall temperature remains constant at 300 degrees Celsius. Neglecting the axial and azimuthal dependence, the maximum temperature in degrees Celsius in the pellet at steady state is dash, rounded off till nearest integer. Okay, so here we have been given that axial and azimuthal dependence is nil. Okay. that means that in the energy balance, for the energy balance equation that we write for the cylinder, all the terms corresponding to uh, z and phi will be equal to 0. So that is, we can write the energy balance across the cylinder. So let's just consider this cylinder. This is my center, and we have been given R over here. So this is at R equal to 0, and this is R equal to R. This is my Z. So we can write the energy balance equation as 1 by R d by dr R plus we also have this heat generation term. So that is Q dot is equal to 0. So this energy balance we have to use to find the maximum temperature in the pellet. But since we are given steady state, so del T by del T we are considering it as 0. And here, what all things we have been given? The diameter is 20 centimeter. That implies R is 0.1 meter. Density we have been given as 6,000. Conductivity K is 300. Now Q we have been given as 10 raised to 4 watt per kg. And the pellet wall temperature we have been given as 300 degrees Celsius. And we have to find Tmax. So let's just solve this equation to find the temperature profile. And once we have the temperature profile, then we can differentiate it with respect to R to find the and equate that equation to 0 to find the maximum temperature. Yes, we can simplify this and write it as d by R Rk Q into R is equal to 0. Now we can integrate this equation with respect to R once, and it will give us Rk dt on R plus Q dot will constant, and the integration of R will be R square by 2. This will be equal to C1. Now let's just find the value of C1. So that is at R equal to 0, that is at the center. We can put the value of R equal to 0. So this will become 0 plus Q dot into 0 is equal to C1. So that implies that C1 will be equal to 0. So yes, we can write this as R K plus Q dot R square by 2 is equal to C1, and C1 was 0. Now we can again simplify this and write it as this R will get cancelled out. That is dt by dr is equal to minus of Q dot R upon 2K. We can again integrate this equation with respect to R to find the temperature variation across radius. So that will give us T is equal to minus of Q dot into R square on 4K plus C2. Now we can use another boundary condition, that is at R equal to capital R, that is at the radius. We have been given the wall temperature as TW. So we can write that as TW is equal to minus of Q dot R square upon 4K plus C2. So from this we can find the value of C2 and put it over here, and we can get the temperature profile as T is equal to TW minus of Q dot R square upon RK plus Q dot capital R square upon, this was 4 This we can simplify and write it as so from this equation we have the temperature profile across radius. Now for maximum temperature we can write that dt by dr is equal to 0. So we can just differentiate this equation and equate it to 0 and we can get 0. Tw is constant, so it will become 0 plus q dot r square 4k to differentiation of 1 will be 0 minus of integration of x square will be 2x and 1 upon r. So this term can't be equal to 0, and also we have been given that r the radius of the pellet is not 0, so this term will only be equal to 0. So from this we can get that at r equal to 0, T will be T max. So to find the maximum temperature, we can put the value of r equal to 0 in this equation. Also, since the cylinder is symmetric, we can just straight away remember it that for any symmetric object at the center, the temperature will be maximum. So yes, we can put r equal to 0 in this equation, and we can get the T max as Tw plus Q dot r square upon 4k. This will be 1 minus of 0. Now we can just replace all the values. So the wall temperature we have been given as 300 degrees Celsius plus Q dot we have been given as 10 raised to 4 watt per kg. So yes, let's just write it as. Now this I need to change into suitable units, so I will just multiply it by the density 10 raised to 4 into 6000 on 4 into k. We have been given as 300 into radius we have been given as 10. Diameter is 20 centimeters, so radius will be 0.1 meter, 0.1 whole square. This will be equal to 300 plus 500 and T max will be 800 degrees Celsius. So yes, the maximum temperature in the pellet at steady state will be 800 degrees Celsius. With the final answer rounded up to nearest integer, we can write it as 800 degrees Celsius. Okay, so we looked upon the last question for today's session related to this cylindrical solid pellet, and we had to use the energy balance equations to find the maximum temperature within the cylinder pellet. So given this axial and azimuthal dependence were 0, we used this equation and then integrated it to find the temperature profile within the cylinder, and then differentiated that to find the location for the maximum temperature and then the maximum temperature within the cylinder that was found by replacing the other values. So and the final answer we had to write it. It was numerical answer type question. We were asked to round up till nearest integer, so we reported the answer as 800 degrees Celsius. So yes, this was all for today. If you have any doubts, I am here for 5-10 minutes, and then okay. So for the for the last question, we are just doing this unsteady state energy balance. So uh, you would have learned those equation for this Cartesian coordinate, that is the what second derivative of temperature with respect to x plus second derivative of temperature with respect to y plus second derivative of temperature with respect to z plus this thermal diffusivity term, that is k upon rho Cp is equal to dt upon time. So the same equation we can write it in terms of this cylindrical coordinates. So from that we can get this final equation that we are using. So these are the notes corresponding to those lecture, and in this, see here we have been given the equations for this cuboid or cube, whatever you consider. Okay. So these equations are in Cartesian coordinate x, y, and z. So similarly, we can find the equations for the cylindrical coordinates, but that will be in terms of r, theta, and z. But in the given question, we were given that the variation across this axial and azimuthal dependence was 0, so that del 2 t upon del 2 z as well as del 2 t upon del 2 theta will be equal to 0. And also this term we had equated to 0 since it was steady state. So from this equation, we get that. Basically, this equation is in Cartesian coordinate, that is x, y, and z, and we have to use the cylindrical coordinate for our case. So in this equation also you can replace x equal to r sine theta, y equal to r cos theta, and then you can similarly get that Cartesian coordinate equation also. Or in other references, you can find straight away this equation in the cylindrical terms. So see, I don't think it is visible or not. So in this lecture 8, they have derived this equation for this Laplacian operator. So we had used this term, the first term, and these two second, the last two terms, these two terms were neglected in our case. So you can straight away use this formula. I guess that answers your question. So I'm just here for a few more minutes. If you have any doubt, you can ask, or else we can end this meeting. And thank you everyone for joining today's class. So I have the recorded lectures, but I guess they will be uploaded very soon on that website. So all these recordings, all these sessions I am recording, and they will be uploaded soon. I'll just confirm with them once, and then we can have this. Or else in the next lecture, I'll just share the YouTube link with you guys in this slide, and then you can check that.